Okay, this is the sixth and final video for today's presentation. And I brought up the equation force equals mass times acceleration. And really all of Newton's laws exist in this simple equation. Just so you know, force is a vector and acceleration is a vector. So that is the vector way of writing that equation, because you'll be using vectors in this equation. Now, I want to bring up a situation that we are most familiar with acceleration and force and mass, and that is acceleration due to gravity. Let's look at it like this. So here is a small cliff, okay? Not a very big cliff. And here's a man taking a dive off the cliff, and he's going to land safely at the bottom and not have any big hospital bills to pay, okay? He's jumping off the cliff. And when he starts to fall, he will experience a force due to gravity, and because of that, he will accelerate. Now, the acceleration due to gravity on Earth is what? Does anybody know? Andre? Right, 9.8 meters per second squared. Now, this is a little bit of a counterintuitive thing. When you feel if you have two objects, say a boulder and a pebble, and you drop both of them off a cliff, is the force of gravity the same on both objects?
Yes.
No.
No.
No, if it was, let's draw, here's a boulder and here's a pebble. I'm going to draw the vector for force due to gravity, Fg. If the force due to gravity was the same for both, it was F the magnitude, it was Fg for both, look what would happen. So if force equals mass times acceleration, let's say the force of gravity was 100 newtons, just for example. The mass of this rock is, say, 1 kilogram. Not much of a boulder, okay? It's just a rock. The mass of this pebble is, let's say, 1 times 10 to the negative 6 kilograms. So it's pretty small. That would be what? What would 1 times 10 to the negative 6 be? How many kilograms? How would you say that? Yeah.
0.000006 or 1.
Yeah, kilograms. And so that would be, anyway, 1 times 10 to the negative 6 kilograms. So it's a pebble.
1/10,000.
Right. It's a pebble. It's small. So we've got 100 newtons. So Fg in this drawing. If we're saying that the force of gravity was the same on everything, force of gravity would, let's just say it's 100 newtons. So got 100 newtons of force. So F equals ma. So the mass is going to be 1 kilogram, and you're going to calculate the acceleration. So we simply divide each side by the mass. So the acceleration equals 100. And that would, of course, be meters per second squared. So that would be the acceleration of the boulder, or the bigger rock. Let's do the same thing for the small rock now. So this one, the force is the same in this drawing. The mass is now 1 times 10 to the negative 6. And so if you divide, I don't know what I just did, but I did something, and it's kind of neat because it made the page bigger. And I probably made a funny squeak on the microphone. So 1 times 10 to the negative 6 1 times 10 to the negative 6. So now the acceleration is 100 divided by 1 times 10 to the negative 6. So, yeah, 100 divided by 1 times 10 to the negative 6. And I get, it looks like I get 100 million as my answer. So 100 million. And that would be meters per second.
So that's fast.
That would be, so, and we know from, so obviously the force of gravity is not the same on every object. The force of gravity must be different because what do we know about falling objects? They all do what? They all fall at, yeah, the same speed in a vacuum. Okay? They all fall at the same speed in a vacuum. So if all objects fall at the same speed, let me move this out of the way. Don't know what I'm doing. Sorry. Just come on over here. Well, it likes that spot, I guess. If all objects fall at the same speed in a vacuum, then the force of gravity must be different on objects of different size. And so remember, people used to think, Aristotle used to think that big objects fell fast and small objects fell more slowly. Well, that would correspond to the physics we just did, which isn't the case. All objects fall at the same speed in a vacuum, and on Earth, generally speaking, two objects that are roughly the same shape, even if they have very significantly different masses, will fall at the same speed. It starts to change when you get to things like balloons because of things like the Archimedes force, which I don't want to talk about, which is buoyancy, essentially. I don't want to talk about it right now, though, so I'm going to stop talking about it. So let's go to the correct physics of falling things and use Newton's equations for that. And it's really neat what happens. So in reality, the way it really works is everything experiences the same acceleration when it's falling. Okay? That's the key. It's called the acceleration due to gravity. And that is on Earth, on the surface of the Earth, it's 9.8 meters per second squared. So let's do our experiment again. Now we'll drop our boulders. And this time, I'm just going to draw the acceleration vector. And this is the same for both. And it's 9.8 meters per second squared, 9.8 meters per second squared. And you need to commit this number to memory. All right? 9.8 meters per second squared is the acceleration due to gravity. So this is A, and it's our vector, A. All right, now let's do the equation. The big rock still weighs 100 kilograms. The little rock weighs 1 times 10 to the negative 6 kilograms. So let's work out the force on the big rock. Ready? Here we go. The force on the big rock equals the mass of the big rock, 100 kilograms times 9.8 meters per second squared. So what's that equal, Michael? 100 kilograms times 9.8. What's 9 times 100? What's 0.8 times 100? It's easy. 80. So what's the answer? 980. Very good. 980. What's the units, Nicholas? No, it's a force. Say it louder. Newtons. 980 newtons. That's the force on the big rock. Let's do the small rock. So this will be FB, or force big rock, big force. Force small is the mass, 1 times 10 to the negative 6 kilograms. times the acceleration due to gravity. So we have 9.8 times 10 to the negative 6th newtons. Small force, right? Small force, big force. Small rock, small force. The trick is they both accelerate down at the same rate. So they're gaining speed going down at the same rate. So big things experience a big force of gravity. Small things experience a small force of gravity. This is very intuitive if you picture it like this. Watch. Let me get a new page here. Oh, how do I make a new page? I thought this was going to be easy, but now it's not. There we go. That wasn't too bad. Okay. Okay, new page. Now, let's picture it like this. Real simple. This is really, really simple. Okay, so here's me lifting something, and I'm lifting a 5-pound thing. Okay? Not too bad. Let's just call it kilograms. Okay? 5-kilogram thing. So it's experiencing some force small, right? And I feel that as 5 kilograms. So now, here's me, and now I've got to hold up something that weighs 50 kilograms. It experiences a bigger force. Force big, right? So because the acceleration due to gravity is the same for all objects, things that have more mass are heavier, and things that have less mass are lighter. But it works out so they all fall at the same speed. The acceleration is the same for every mass. And I'm glad you said weird, Nicholas, because it actually is a deep physical principle called the equivalence principle, which we'll talk about later. And as far as I know, there is no explanation for the equivalence principle. But anyway, leaving that aside, the acceleration due to gravity is the same for all objects. And for smaller objects, the force due to gravity is smaller. For bigger objects, the force due to gravity is bigger in proportion. Hence, all things fall at the same rate. Now, I'm going to post some videos following this that you need to watch from online sources, and they'll explain some of these things a little bit more, and then there'll be some other things to look at in the lesson, and a reading assignment as well, and then an assignment from the book. And if you are feeling lost, I want you to email me, and if you are physically lost, you need to call 911. I guess. If you don't have a cell phone and you are lost, then you're probably not watching this video either. Okay. Anyway, all that aside, if you're having trouble, give me a call, and we will have questions ready for lab so that you can ask me questions regarding all of these things. Okay. Goodbye.